So I'll pause for a moment and let you think about this problem. But the first thing to notice is that it's quite a general problem. ABC is any triangle. It's not concrete. It doesn't give you anything about the specific coordinates or the specific side lengths. There is a general statement that the length of AB is equal to length of AC, which is the only premise that we have about the triangle. And we want to prove quite a general result, namely that two abstract angles are equal. Now, given especially the pictorial depiction of that triangle, our intuition for proving this is that we want to use the symmetry of the triangle in some way. Namely, we want to be able to cut the triangle in half and be able to match the angles ABC and BCA. And of course, if I were to be able to print out this triangle and cut it out, then I would just fold the triangle in half and see that the angles match. Unfortunately, that does not constitute a mathematical proof. To have a full mathematical proof, you need that every single step in your deduction is an irrefutable truth. So for a full mathematical proof for this, well, it would look something much more like this. You start with an auxiliary construction where you construct a midpoint on the line BC. Then from that, you can construct this segment AD, and that gives you two triangles, ABD and ACD. And by hypothesis, you have that the length of AB is equal to the length of AC, and the length of BD is equal to the length of CD. And as AD is a shared side, by the axioms of Euclidean geometry, you can conclude that the angle ABD is equal to the angle DCA. We're not done yet at that point, because what we actually want is that the angle ABC is equal to the angle BCA. However, since our point D was a midpoint on this line BC, B, C, and D are all collinear. And that allows you to conclude that angle ABD is equal to angle ABC, that angle DCA is equal to angle BCA, and therefore we get our equality, that angle ABC is equal to angle BCA. Now, there are several things to take away from this proof. It's quite a simple problem statement, but most critically, in order to be able to solve this problem, we had to introduce an auxiliary construction. Namely, we had to introduce this midpoint D in order to be able to solve this problem. Another thing is that we used this auxiliary construction, this notion of this midpoint, with an implicit second premise, namely that this midpoint that we construct is going to be on this line BC, and therefore is going to be collinear with B and C. And so in order to be able to solve a problem of automated theorem proving, we can see that there's two simultaneous problems that we need to solve, and we need to solve both of them incredibly well. One is, of course, the first problem, which is that we cannot just use human intuition to be able to deduce the proof. We need that every single step is irrefutably true. And the other is that we need to be able to introduce auxiliary constructions, because not every single step of the proof, even if we do want everything, even if not every single step of the proof can just be deduced from the premises as they are. You might have to introduce some additional constructions, which are absolutely true, but which are not in the statement premise. So when we look at an IMO problem, which is the monumental feat that AlphaGeometry was able to solve, well, we're not going to actually break down this problem, and we're not going to solve it, but you can see that there's quite a large number of more premises inside of this problem. So there's going to be quite a lot more deduction steps. And also that the statement that we are asked to prove is quite a lot more complex. And so we would be asking for a lot more auxiliary constructions along the way. So in order to develop the system, again, these two problems, having solid deduction steps and having really great auxiliary constructions are the two parts to be able to solve. So let's focus on the first one. And for the first one, we can go back and look at the more traditional technology, namely symbolic engines, to be able to find a solution for this. A symbolic engine, every symbolic engine is predicated on what is called a symbolic grammar. So a symbolic grammar is a specialized language for encoding symbolic problems into an interpretable syntax. An example of a symbolic grammar is shown below, and this is a particular symbolic grammar that is useful for encoding geometric objects and predicates. and it has been used by symbolic engines such as gex, JGEX, MMP, and so forth. What the symbolic engine does is it uses the symbolic grammar to be able to make deductions, much in the same way that, well, in a similar way, or at least similarly analogous to how a computer is able to use the strict syntax in a programming language. The simplest symbolic engine that you can construct is known as a deductive database. So this is a type of a relational database such that new facts can be derived based on the information that is stored in the database. Now, you don't have to have a lot of knowledge about relational databases to understand what this is doing. And that's the key thing that we need to understand. Namely, what this is doing is it's taking some statements in the symbolic grammar, it's chaining them together based on what are, well, in the case of geometric reasoning, based on what are called definite horn clauses, and it's producing new predicates which are necessarily true. So some example of some predicates and some rules that you have for deductive reasoning are below. These are directly from the paper by Chao Gao Zhang, such as, for example, rule 1, which the chain of reasoning actually goes in both directions. It's an if and only if statement. So you can have P or Q be either one of the two statements, but let's take the predicate to be that AB is parallel to CD. Then one rule that you can have is that for any PQ, the angle between AB and PQ is going to be equal to the angle between CD and PQ. Now, granted your set of predicates and your set of deduction rules, at this point, deductive databases are a very efficient piece of technology where the deductive closure, so all conclusions that can be found from a set of predicates, can be found in a matter of seconds on a standard non-accelerated hardware. So let me delve a little bit more into what this deductive closure is so that we understand the complexity of what that means. When you have a list of K predicates, let's take K to be 3 so that we can make this very, very explicit. All the conclusions that you get are going to not just be the conclusions that you can derive from every single one of the statements, P1, P2, P3, necessarily having to be used to draw a conclusion, but from all subsets of them as well. So one conclusion would be the predicates themselves, because P1 is a conclusion from P1 itself. P2 is a conclusion from P2 itself, and so forth. You also draw all the conclusions from P1 and P2, P2 and P3, and P1 and P3, and of course from all of them. And further, as you draw conclusions, you can add them into your list of predicates, and you draw more conclusions. So it's quite a complex, it gets to be a very, very, very highly complex problem that can be solved at this point in a matter of seconds. Now, deductive databases are incredible for deductive reasoning. However, they do have their limitations. One limitation is that they're not very good for any type of a numeric problem. Namely, whenever you have to compute a very specific quantity, it's very hard to be able to encode something like that into a deductive database. So what another type of symbolic engine, and this was developed by Google DeepMind, is an algebraic reasoning module. And this is of a very different flavor. Namely, it's able to cover any type of computational problem. Mostly for these IMO geometry problems, to be able to cover angle chasing, ratio chasing, and distance chasing. What it does is it converts a geometric equality into linear equations and then uses a Gaussian elimination technique to be able to solve them in order to be able to get new relations. I think the best way how to just see what the algebraic reasoning module does is to look at this example, where the goal over here is to be able to find an exact value of this angle, EXF, in this problem statement. And you use many of the relations that you have that you know from the problem statement about relations between the values of angles in order to be able to deduce through a process of Gaussian elimination what the angle at EXF exactly is. So for solving IMO geometry problems, you'll need both deductive reasoning, which is the axiomatic aspect of geometric reasoning, and algebraic reasoning to be able to solve the numeric aspects of problems. And so a complete symbolic engine to be able to solve these IMO problems would construct proofs using both a deductive database and an algebraic reasoning module. Now, the way that Google DeepMind has been using it is by alternating between the two of them. So you construct the next step in the deductive closure first with the deductive database, then with the algebraic reasoning module, and so forth, and you alternate between them. Now, there are a couple of details on this slide about the presentation of the data. We're going to get much more into that. What's important at this point to take away is that what you get from a deductive database and an AR approach is that you can, given a set of premises, completely solve to a conclusion one of these problems, which allows you to then, you can completely solve to conclusion one of these problems. However, you need to have the correct set of premises in order to be able to solve to the conclusion that you desire. And so the main problem that AI needs to solve at this point is to be able to construct auxiliary proofs and to construct auxiliary premises to be able to inject them into a symbolic engine and to inject them appropriately, relevantly, and in the correct symbolic grammar. So that's, I guess I already gave it away. That's where the AI comes in. And so to do proof search together with transformers, you construct an engine as follows. You start with a problem. We have the simple problem that we've already seen at the very start that you can inject into your symbolic engine. If the symbolic engine is able to solve it, then you're done. If it is not able to solve it, then you query the language model for additional premises that it will add to the problem statement, and then you add it into the symbolic engine again and attempt to solve it. And you keep looping until either you solve it or this process times out. Now, the IMO is a timed test for humans, so it makes sense to make it be a timed test for AI as well. So as you can see, with this IMO problem 3, 2015, which we saw a few slides back, there's quite a few auxiliary constructions that are necessary to be able to solve it. So purely solving this problem with the problem statements as it is given, using only the symbolic engine is not possible. And so the goal of AlphaGeometry and the goal of the transformer is to be able to make these exact auxiliary constructions and to make them and to inject them at the correct step in the procedure. So a little bit more detail on this before we get into the specifics about training and about setting up this transformer model. So again, the transformer-based proof search or AlphaGeometry is a loop between a symbolic engine and a language model, where for querying the language model, you seed the language model with the problem statement string, and you add at each step an auxiliary construction, and you pass that to the symbolic engine. Now, in order to make this perform really well, for model decoding, you don't just query for one answer at a time. As great as the training procedure is for AlphaGeometry for this transformer model, usually, very often, the first answer that you get, especially when you need it to be so precise, is not necessarily always the best answer. So what they do for model decoding is they perform a beam search on, well, 512 alternative constructions at every single step. They have 16 maximum iterations with a branching factor of 32. And this is a very computationally expensive procedure to be able to correctly deduce a problem. And so they run this on 4 V100 GPUs, each of which hosts a copy of the language model, and also 10,000 CPUs, which host the symbolic engines. At the end of the day, the output that you get after you adapt the problem statement in the appropriate symbolic grammar is a complete proof that looks something like this. And it's very close to human readable. At the very least, it's human interpretable. And it can be verified by a human whether this proof is correct or not. So the key thing at this point for the transformer model, in order to perform well, is that it has to be able to, the problem that it's solving is, of course, that it has to construct this auxiliary construction, but it has to give an auxiliary construction in the process of solving a proof such that it is in the correct grammar, so that it can be interpreted by the symbolic engine, and so that the auxiliary construction that it provides is going to be relevant to the proof. For the first problem, as some of you who have worked with transformers or even just played with ChatGPT might know, with very elaborate prompt engineering, you might be able to solve that problem of being able to always get a language model to produce responses of a very particular type of a grammar, namely in the symbolic grammar that you would want. At least for a large enough model, for an elaborate enough prompt, that is a problem that you can solve. However, the problem of relevancy still remains an open problem and cannot be solved purely by prompt engineering. And so this is where Google DeepMind comes up with a very innovative approach to train a transformer from scratch to be able to provide auxiliary constructions to the symbolic deduction engine. And so for this, they generate a massive amount of synthetic data. So remember, the point of the language model is that it communicates effectively with the symbolic engine. And so that it communicates effectively with the symbolic engine to be able to solve proofs, it needs to be feeding statements into the symbolic engine. And so the data that it will need is going to be data that is in the appropriate symbolic grammar and follows a sequence of steps which mimic the deductive rules of the symbolic engine. And so the synthetic data that you generate comes from the symbolic engine itself. Now, on a high level, the way that you generate this data is you start by a random selection of proof premises. You feed that into your symbolic engine. And so the way that you choose these proof premises, of course, you have to make sure that they are mutually non-contradictory. So you do uniform random sampling one at a time, checking that the statements that you start with are not contradictory. For example, contradictory statements in Euclidean geometry would be that the line AB is perpendicular to the line CD, and the line AB is parallel to the line CD. And you cannot have both of those to be true. So you select them one at a time so that each new statement that you have in your premises are going to be not going to contradict your previous premises. And there's a whole list. They claim to have 1 billion such premises from which they sample. From this, you generate all possible conclusions using the symbolic engine. So this is the massive complexity that we talked about before, where you generate every single possible conclusion. So this enormous graph given a set of premises. Now, they don't use the entire graph for training, and there are many reasons for this. One of the most important reasons for this is that if you're generating all possible conclusions from some random set of premises, at some point you might have some amount of, there are ways that you can ensure that you don't have redundancy in the proofs as far as that the proofs that you generate are going to be unique. You might have some redundancy in proof steps, such as transitivity redundancies, like A is equal to B is equal to C, therefore A is equal to C. You have two steps before you get to A is equal to C. And so if you can arrive at A is equal to C much more quickly than by arriving first at A is equal to B and then B is equal to C, then you would put a preference to only the branch at which you arrived at A is equal to C, if that's the conclusion that you need. And if there's a shorter way how to do that. So there are traceback algorithms as they're doing the forward inference and constructing these graphs to be able to find the minimal deductive closures so that you have the shortest possible proofs, which are still going to be accurate to the problem that you wanted to solve. Well, which are still going to be accurate at every single step. So you don't trace back and take away steps that would make the proof inaccurate. You would just take away steps that makes the proof verbose. Then there's a very complex processing step for these graphs that you generate. The most important step in this processing step is that you determine what are the dependency differences in this graph. So you have a set of premises, you have the conclusions that you reach, and you have your dependency subgraph between your premises and your conclusions. Now, when you look at the conclusions, not every single construction that was in the premises necessarily appears inside of the conclusions. And then in this case, you don't get rid of the premises because the premises could be necessary to be able to solve that conclusion. But what you do is you move the premises into the dependency subgraph so that it becomes a part of the proof and not that it is a premise in the problem. And so that in this way, the model is going to be able to learn how to do auxiliary constructions. So we're going to go into all of this a little bit more. So let's start with the very first step and just take a look at a couple of proof premises that are going to be constructed. So proof premises generally look like this. These are in human-readable form. Of course, they're translated into the symbolic language. They come in a form such as construct a point X on the angle bisector of ABC, or construct a point X on the line AB. This is maybe about only a third of the proof premises, of the general statements of the proof premises that were tried by AlphaGeometry in this synthetic data generation. There are some which prescribe specific values, say specific values to angles, which are not on this list, which is necessary for algebraic reasoning problems. And so by varying ABC and varying the values of those angles, side lengths, and so forth, you do start with a set of 1 billion of these. Now, you sample some of them randomly. Not all of them are going to be sampled to get such a nice geometric figure, but for the purpose of illustrating this diagram and illustrating how the data is constructed, it's nice to start with a nice diagram. So the premises that you have are depicted by this diagram, and they're going to be something along the line of that ABC is a triangle. You have these perpendicular lines BD to AC and CE to BA. You also have this line AF, and so forth and so forth for every single, and you have some intersections, say it's C and G, and so forth and so forth. Now you construct the deductive closure. So again, you take these premises, you find all the possible conclusions, such as, for example, you can find a conclusion that EADH have to be cyclic, from which, if you include this with the previous premises, you can further deduce that the angle EAH is equal to the angle EDH. And then you can even further reduce that HA is perpendicular to BC, which it seems like we would want, but it's not explicitly stated in the premise. Now, so now you can take any of these elements which were deduced, and you can say that that's the conclusion of the proof. We're generating synthetic data. We're generating proofs at this point. So any of these conclusions can be the conclusion of the proof. So let's take HA is perpendicular to BC as the conclusion of our proof. Now, in order to be able to now reconstruct the entire proof, we start with a set of premises, and we want to look at every single chain that we had to follow in getting to this conclusion. And every single one of those chains is a complete proof to get to this conclusion. Now, there is a traceback. We're going to talk about that a little bit on the next slide. But what I want to point out is the part of moving premises into the proof when they are not used in the conclusion. So when we look at HA is perpendicular to BC, something that we can notice, which is actually in every single one of these proof paths to be able to get to this conclusion, is that you needed to have the auxiliary construction of E and D in order to be able to make this conclusion. E and D always appear in every single one of these proofs. Well, I guess not in this last one. Only E appears in that. But E and D appear as auxiliary constructions because you don't have E and D in this statement over here. And so however, the construction of E and D are necessary in order to be able to get this conclusion. So when you flatten this graph and you construct the proof, you take all the premises except for the ones that include E and D as the premise of your problem statement, and you put as the proof step that you construct E and D. And then you follow these proof paths after that. And in this way, when you're conditioning, yes, that's a very good question. And so in this way, when you're conditioning the model to be learning based on the theorem and the conclusion and learn to construct proofs, it's going to learn how to construct auxiliary steps inside of the proof. So there is a question that I want to make sure that I address. How is the choice of conclusion decided? Is it at a certain depth, and what other factors? Yes, that's a very good question. You do it at all depths. Effectively, you do it at all depths. So at every single step of this generation, you can take any one of these conclusions as the conclusion, and you actually do it at multiple depths. So you first look at the premises themselves. They're their own conclusion. That's a trivial proof. You can take one step, then two steps, then three steps, and so forth until you get the full deductive closure. And so you're looking at any one of these as being a potential proof conclusion, and any one of these branches to any one of these points as being a proof that you add as a complete proof, as theorem statement, conclusion, and the proof path that you add into your data set. And so in particular over here, we would have from this, if we select this to be a conclusion, we would have 1, 2, 3, we would have 3 proofs if we select HA is perpendicular to BC as our conclusion, but we also add those proofs that have EC is perpendicular to EA as a conclusion, similarly with any one of these steps. So there's quite a large number of proofs that you add. Yes, so the gray nodes over here, those depict other proof paths. So those do not end at HA is perpendicular to BC, but yes, those are included as well. Absolutely, those are included inside of the data set as well. They just don't end at HA is perpendicular to BC. Yes, so you take the full deductive closure completely until you get all the terminal conclusions. Okay, so this graph that you're constructing is massive, and so this is where you want to do some type of traceback, because you really can get some dependencies which are, while every single step is true, might not be necessary, or there might be like a shorter path to it. And so the traceback algorithms are quite complex. Namely, for the deductive database reasoning, it's to be able to get rid of circular dependencies, such as A is equal to B is equal to C, and A is equal to C. And there is some description inside of the paper about how this traceback algorithm is constructed. The full solution for these types of dependencies turns out to be an NP-hard problem. So there are some greedy solutions for this. While for the algebraic reasoning module, the deductive to be able to find the minimal set in the deductive closures reduces to a linear programming problem. Let me address any details about these in the questions, since they are quite complex. But the point to really take away is that this is a very complex part of the procedure. It's not equally solved part of the procedure, so you can potentially get some redundancies inside of your proofs, in the sense of, like, some meandering, some verbose proofs. But it's your best attempt solution in order to make it to be not verbose. And there's one last step to there's one last step to pruning, to making your data set a little bit, well, not your data set, but the graphs a little bit smaller, which is pruning every single premise that is unnecessary to reach the conclusion. So if you remember, when we were constructing these deductive closures, we could take, when we were looking at like P1, P2, P3, we would be looking at all conclusions, not just from all three of them being necessary, but say from any two of them or any one of them being necessary. If you have a proof where only two of them are necessary, then and say P1 and P2 are the only ones that are necessary, then you prune every single branch that is making deductions using P3 as long as it's not necessary. The point of this step, and this is also a very hard procedure, and it's done by trial and error. The point of this step is that you want auxiliary constructions. So you want your model to be able to learn auxiliary constructions which are relevant. And any premise that is not going to be necessary to reach a conclusion is an auxiliary construction, but it is not relevant to the conclusion of the proof. And in this way, you're restricting the data set so that you're restricting the infinite space of auxiliary constructions that you can tag onto any problem to only that which is relevant to constructing a conclusion for a proof. So there's a nice graphic that they have for the distribution of the synthetic data that they generate. Namely, by the traceback algorithms and by the pruning, you do have that quite a large number of the synthetic data that you generate are going to be centered towards very short proofs. So very few proof steps. You can start with a trivial, you do have quite a large number of trivial theorems. That's where all the premises are just their own conclusion. But you do get maybe like around here at, between like 20 and 40 proof steps, some well-known theorems and some close to IMO level problems. But you also do get some very, very complex constructions, such as over here, you have a proof length of 247, every single step being necessary, and every single premise being relevant to this construction. Now, what's also interesting is that when you look at the entire distribution of the data, and you're starting with this random sampling of proofs, and so remember, you start with a random sampling of premises. You construct these deductive closures, and then you look at the conclusions, and any premise that has a construction that does not appear in your chosen conclusion becomes an auxiliary construction. Now, it's interesting that only about 9% of the data actually has these auxiliary constructions. So they generated 100 million of these. They generated 100 million of these proofs. None of them are duplicates of each other. None of them cover any of the IMO problems, which they also checked against. And only about 9 million of them actually have auxiliary constructions inside of them. And so this is where, in order to be able to, and only about 9 million of them have like the auxiliary constructions inside of them. And so this is where, in order to be able to give the model a large preference towards auxiliary constructions, they do an additional fine-tuning procedure on the data that they generate, which has auxiliary constructions. So they do start by pre-training a model from scratch on only a vocabulary which has the symbolic grammar. They have a relatively small model of only 151 million parameters that they train on the full 100 million synthetically generated proofs. And they further fine-tune that on those about 9 million proofs which have auxiliary constructions to give that preference in the model. They do train a custom tokenizer for this on a vocabulary size of 757, which is entirely just on the symbolic grammar. This ensures that the model is only going to be speaking in the symbolic grammar, so you don't have to have any fancy prompting in order to be able to speak in the symbolic grammar. And there's a couple of other statistics that they have about how they about how they train their model. And there's quite a bit more in the paper. So please feel free to check that out. But let's move on to the most interesting part, which is evaluating the performance of this model. So let's quickly summarize what we have at this point. We had, from the beginning, a symbolic engine which is able to deduce proofs, where every single step is going to be necessarily correct, but it does not necessarily have to reach the conclusion if it doesn't have the right auxiliary steps. Now we have a language model that we have integrated together with the symbolic engine so that it feeds it auxiliary constructions. And we've trained this language model so fully on the symbolic data. And we've trained it so that it learns relevant auxiliary constructions. We've fine-tuned it so that it learns relevant auxiliary constructions. To evaluate the performance of this, you use the expert human evaluator, namely Evan Chen, who is a coach of the IMO team here in the US, who has scored and graded many of these IMO exams in his life. The evaluation dataset is a brand new evaluation dataset, which Google DeepMind calls IMO AG30, which consists of 30 IMO geometry problems, which were used in the actual competition since 2000. Again, none of the 100 million synthetically generated proofs in the dataset overlap with these IMO problems. The models that you're evaluating against this evaluation dataset, such as AlphaGeometry, is evaluated either 0 or 1 for complete correctness, and it's evaluated by a human. No intermediate points, no partial solutions are given to the model. For human test takers, though, taken by human performance in the past on the IMO, humans are actually scored for partial scores, for partial points. Their score, human performance is, for human scores, they're scored out of 7 points. And so to compare model performance, you take the human scores and you scale the human scores linearly so that 4 out of 7 becomes 0.57, and you compare those scores against the model score. So just remember in this comparison that the models are not given partial scores. They're not given any partial credit if they get some so-called partial correctness of the proof. Some of their baselines are some previous automated theorem solvers, as well as the strongest baseline that they have, which is just a symbolic engine together with some hard-coded human heuristics. So they don't provide what the human heuristics are, but you can imagine that these are that, for example, if you have, say in our first problem, 2 lengths of a triangle to be equal, you would want to add some type of symmetry statement, such as constructing a midpoint as an auxiliary step. So these are hard-coded human heuristics that are used with DD and AR. This is their strongest baseline that they're testing against to see if the AI is able to provide something better than a hard-coded human heuristic. And I also want to point out that they also compare to the best to-date theorem prover, which is known as Wu's method, which is a completely different type of a method known as a computer algebra system. It does not use a symbolic engine. It does not use AI. We're going to take that as a black box since it's a very different approach to theorem proving. And we're only going to be using that as a comparison to see, well, how well AlphaGeometry performs. So the moment that everyone has been waiting for, the results. So out of the 30 problems, Wu's method is able to solve 10 of them. GPT-4, when you just prompt it on these problems, is able to solve absolutely 0 of them. When you look at just a deductive database combined with the algebraic reasoning module, you're able to solve 14 of them. That means that 14 of these problems can be solved purely by deduction based on the premises. When you add some GPT-4 auxiliary constructions, well, you're only able to solve 1 additional one. So that's very specific prompt engineering for GPT-4 to give me an auxiliary construction, it only is able to solve one additional one. With human design heuristics, you get 18, which is nice. Well-coded human design. This is hard-coded. This is not human intervention in the sense of live saying now add this as an auxiliary premise. These are a priori hard-coded things, heuristics, prior to so that no human is actually live involved with this. And then lastly, you have AlphaGeometry, which has an impressive 25 out of 30 performance. Without pre-training, so only fine-tuning, it still has 21. Without fine-tuning and with only pre-training, it still has 23. And so compared with humans, well, an IMO gold medalist would have approximate score of 25.9. AlphaGeometry is just shy of that at 25, and it certainly beats a silver medalist, which is at 22.9. So there are a couple more results that are more. There are a couple more results about this. The most important one that I'm going to be focusing on is what happens when you vary the training data size. So remember, you trained this model. It's a fairly small model, but still you trained it on quite a large amount of data, on 100 million of these synthetically generated proofs. If you train it on only 20 million, you still get 21 out of 30 correct, which is still better than, well, it still is better than the next best thing, which is DD and AR together with human designed heuristics. So using a transformer that is very, very specially trained on symbolic data with this and further trained for for relevancy of auxiliary constructions is even with a much smaller data set is a much better solution than hard-coded human designed heuristics. What's an interesting graphic is to note what is relatively difficult for AlphaGeometry versus for a human. Now, you measure something as being difficult for a human if they scored low on the problem. And you measure something as being difficult for AlphaGeometry if the number of proof steps that you have are going to be very long. Remember, AlphaGeometry is effectively a very glorified proof search engine. And so the longer a proof step is, the more, and especially the more auxiliary steps that you have to construct inside of it, the more difficult it will be for AlphaGeometry to be able to arrive at the correct proof. So there are some problems which are hard for both humans and for both AlphaGeometry. And there are some problems which are easy for both humans and for both AlphaGeometry. But there is a middling range over here, especially these over here in blue, which are very easy for AlphaGeometry, but seem to be quite hard for humans. And what's interesting is that these are actually deduction only. It wasn't necessary for AlphaGeometry to introduce even a single auxiliary step. And so that's a pretty interesting result over here. Yeah, so knowing how to put together the premises it seems to be a difficult task for humans. Another thing that is highlighted in the paper, and this is particularly interesting to me as a mathematician, is that AlphaGeometry with this method is able to discover generalized theorems. So what this means is that in this instance of the IMO problem, problem 1 in 2004, I was able to identify that in the premise of this problem, there was a statement that was unnecessary to be able to derive the conclusion. So if you put down all the premises, the theorem that it's proving is on a diagram like this. But what AlphaGeometry discovered was that you actually don't need this premise that you need this midpoint O. You just need the diagram to be much more simpler like this, to be able to arrive at the same conclusions. Now, that's interesting because this previously was not discovered. And there's many cases in mathematics, both in mathematical problem, like competition problem solving, and in mathematical research, where people add additional premises because they believe that it is necessary to solve a problem. And it makes maybe some of the steps easier for us as humans to think about it, but is actually unnecessary. in the grand scheme of things to be able to solve the problem. So for example, in the original simple problem, I could have added as a premise something about that D is a midpoint, but it's not necessary to add that as a premise. It's something that we introduce in the process of solving the proof. However, it's something that we introduce in the process of solving the proof. However, as these problems become more and more complex, it becomes harder for us as humans to realize what is necessary and what is not in order to be able to solve a problem. And I think this is an enormous advantage of building out a theorem solver like this, which has enormous implications for research mathematics down the line, that it can help identify, it can help researchers identify what are necessary premises and what are not necessary premises in the proofs that they construct. All right, so I want to conclude with a few future directions that are stated in the paper, and also some future directions that I think are interesting to look into. So the paper does talk about adapting this to other types of problems which rely on symbolic reasoning, and where the problems rely on some auxiliary constructions. And there are several areas of math which have this that have not been explored yet in such a framework, such as inequalities, combinatorics, solving equations, or the field that is the nearest and dearest to my heart, number theory. And of course, I'm certain, and the paper mentions this too, that outside of mathematics too, within some realms of scientific reasoning and scientific computing, this method can be also adapted. So something also to point out that the paper mentions but does not utilize is that there are some quite advanced theorem provers out there, such as Lean. So Lean is a functional programming language that functions as an interactive theorem prover, and it has already been partially adopted by the math community. The reason why this has not been used in AlphaGeometry, and rather the symbolic, a more classical symbolic language, more classical symbolic engine, which uses a deductive database and a very classical symbolic language for geometry proving, is because Lean has not yet been adapted to classical geometry problems. It's an ongoing work. It started in 2013. And it's now on version 4, and it's an open source project. There's a whole community. You can contribute to it. And it has been adapted to many areas of mathematics, unfortunately not classical geometry, but many areas of mathematics, including some very cutting edge areas, such as the capsid problem, perfected spaces, and so forth and so forth. And so what would be very interesting would be to see, well, how AI can be integrated together with Lean for theorem proving, for theorem verification, or even for generalizing theorems in a way that could be useful for research mathematicians. And I'm going to end over here and open the floor to any questions.